Hello. Well, we've successfully built a point distribution model of our T, and we've also seen a fair amount of the technology that goes into building that. And what we'd like to do now look at is step back a little bit and sort of see how that all went. Okay, well, we could see that it worked most of the time, but occasionally there were some failures. And a lot of the failures were related to getting the correct number of points on the model. The point distribution model of the T assumed always that we were going to have 8 data points going around that object, and sometimes our segmentation process didn't give us that 8. So in that case, we had to eliminate those examples immediately, even though they may have been perfectly good examples. So that's an area where we could improve, look at a more robust type method for finding the corner points. Another issue also relates to finding those corner points. Sometimes the segmentation algorithm did find the 8 points, but one of those points maybe wasn't in a very good position. Maybe this is related to the shadows, maybe it's just sort of part of the variations of the algorithm. What we would really like for our point distribution model to encode is the natural variations of the shape, not the kinds of error, instead of the errors that our algorithm makes, although that's maybe a useful thing to model as well too sometimes. But really what we want to do is we want to capture the natural variation of the shapes. And then finally, we noticed that in order to build our point distribution model from the particular sample, we need to align all of the shapes into a standard position and orientation. And sometimes the shapes might be a bit too extreme for our heuristic algorithms to be able to align those shapes into that standard position. It's just the algorithm will break down sometimes as well. So all of these present some of the limitations that we've encountered here. We built a model of these T-shapes. It's just a polygonal type objects. They're quite simple, but it turns out we can also extend this kind of technique to much more realistic type problems. Certainly we can extend it to smooth curves, as you saw with the hand example, and we can also extend it into 3 dimensions. People have built models of objects off of ultrasound data and also off of magnetic resonance imaging and CT type data as well. So you can look at the natural variation of, for example, organ shapes like the heart or one of your ventricles or your brain as a family of shapes again. And you can look at the range of the normal mean shape, and you can also look at the range of variations between different people. What made all of this possible really is the use of the correlation matrix, the covariance matrix, as part of the principal component analysis. It looks for the correlations between the shapes, and really it's the correlation between point pairs, the pairs of the features, the x and y coordinates, and also the pairs of points. Well, what about if you had triples of points? Okay, could you not look at some sort of joint-wise variation between all of those rather than just as pairs? So that may be a way of extending the kind of analysis. Here we looked only at the positions of the objects, and one could also look at vectors of other kinds of things. For example, one can treat the image as a vector, and in fact that's what we're going to look at in another example coming up shortly. One of the nice things about this is that we don't need to depend on our training samples being in any particular order. So that gives us some algorithmic advantages, and again that's going to be of useful when we look at the next sample. Well, what have we done here? We've gone quite a long ways, starting at our binary images, or even the original grade level images of a set of shapes. And we've gone all the way through to building a model that encapsulates the natural variations of those shapes. And it's also given us an algorithm to be able to say, when we have a new sample, whether this is one of the examples of those shapes or whether it should be rejected as being a different shape or perhaps being too extreme. As part of that, we used the principal component analysis method, and that was useful for decomposing the important variations from, let's say, the noise variations that we've embedded in the shape. This kind of use of the principal component analysis is quite a common technique in computer vision. It's quite an important technique, so it's useful to know and to use. Thank you very much.